Good morning to esteemed professors, R&D engineers, RF engineers, antenna engineers, communication engineers, research scholars, and beloved students. First and foremost, I would like to thank all of you for joining my webinar in spite of your busy schedule. And I welcome you all to my webinar on mastering 5G millimeter wave beamforming and phase stereo antenna design, which will be presented by me, Divyashree M, with PhD in RF filters and currently working as an application engineer for high frequency electromagnetics at ARK Infosolutions Pvt Limited, the channel partner of Ansys, part of Synopsys now. Ansys stands number one in simulation as it sheds light on bridging the gap between possibility and reality in our day-to-day life in various domains. Indeed, Ansys has more than 90% of customer satisfaction with more than 6,500 full-time employees and 90 plus offices worldwide, with a proven revenue of $2.54 billion USD. Ansys being number one in the simulation world for more than 50 plus years, has made 29 strategic acquisitions, and also invested more than $5 billion dollars in the acquisitions with 350 plus technology partners, including Fluent, Granta, Apache, Microsoft, Zemax, Dyna, Rocky, and many more. And now we are moving on to the core part. Why do we go for simulation? Here's a short video from Ansys.
What do the world's most visionary companies have in common? A superpower. To see the future with absolute certainty. The power to design, to test, and to predict the performance of the most complex products in the universe, all before a single physical prototype is ever built. They summon the world's most powerful engineering simulation solution.
I hope you enjoyed the video. And now I would like to add some flavors to the video. Why do we go for simulation? The first and foremost reason we go for simulation is one can predict the behavior of any component or a system or a device or even the scenario virtually before the prototype is brought into existence. On the other hand, if the prototype or the product is not performing well, engineers can use powerful answer solutions to optimize its performance. And by doing so, the time and cost of a product development comes down drastically. In case if a product fails, we can analyze the in-depth reason for the product failure using powerful answer solutions. And finally, when every product comes to a market, has to comply with certain standards like electromagnetic standards, that is FCC, ISO, CISPR, MIL, etc., in order to ensure the safety of the equipment, the person, and also the environment, where all these simulations are virtually possible by powerful answer solutions. To perform such powerful answer simulations, Ansys has simulation portfolio that broadly covers various domains. In case of semiconductors, Synopsys and Ansys has solutions like Redac-SE, Electrothermal, Totem, PowerArtist, Raptor-H, Raptor-QU, Exalto, Olds RF, Pathfinder, PathFX, ClockFX. For performing simulations that is related to embedded softwares, you have SCAD-based packages from Ansys like SCAD Suite, Display, Vision, Artist, Test, and Lifecycle. And when you are interested to perform simulations related to safety analysis, Ansys provides many Medini-based packages like Medini Analyze for cyber security, and also semiconductors. Under structures, you have Ansys provides solutions like mechanical, LS Dyna, forming, motion, Sherlock, and other solutions. Under fluids, Ansys solutions like Fluent, CFX, Rocky, Turbo Tools, etc. can be utilized. Moving on to electronics, which is our laser focus today, Ansys provides solutions like HFSS, Maxwell, SI-Wave, IcePack, MotorCAD, Q3D extractor, New Hertz, AMA 3D cable, EMA 3D charge. Among this, MotorCAD and Maxwell comes under low frequency electromagnetics, and remaining solutions comes under high frequency electromagnetics. And for optical domain-based simulations, Ansys provides solutions that are related to SPIOS, VR experience, numerical-based packages, and also ZMAX packages. And when the user is interested to perform simulations that are related to materials, Ansys packages like Granta MI, Granta Selector, Granta EduPack, Granta MDS are prominently used. And for AV-based simulations, Ansys provides softwares like AV Accelerate Headlamp, AV Accelerate Sensors, and AV Accelerate Autonomy. And when you're interested to perform mission-level simulations, Ansys solutions like System Toolkit, Orbit Determination Toolkit are broadly used. For performing sound-based simulations, Ansys has a special software called Ansys Sound. And to perform optimization, which is a very critical step in a product development, you have Ansys solutions like OptiSlang, Minavera, and Model Center. And under digital twin, which is the virtual representation of any physical asset that will be connected to some sensors to monitor its performance for seamless connectivity. To perform such digital twin simulations, Ansys solutions like Twin Builder and Twin AI are used. Moving on to 3D design, where you can perform simulations, like you can alter the 3D design instantly and also look at the results instantly using Ansys solutions like Ansys Discovery and Space Climb. And special software from Ansys to perform cloud-based simulations, where you can perform simulations over the cloud that will reduce the simulation time and also the hardware requirement. Yeah. Simulation is ubiquitous, where you can find its applications starting from consumer electronics to space. Moving on to high frequency electronics product collection. First comes HFSS, which is high frequency structure simulator, a powerful 3D simulation software for designing, analyzing, and optimizing RF and microwave components, including antennas, filters, waveguides, PCBs, ICs, connectors, etc. And then comes HFSS IC, which deals with the simulations that are related to multiphysics and multi-scale platform that are related to integrated chips. And there is also Q3D extractor, a special software to extract the parasitic RLGC, which is resistor, inductor, capacitor, and conductance parameters from the interconnect structures. And special software from Ansys to deal with the thermal-based simulations are IcePack, which performs its simulations in the PCBs, ICs, electronic systems, and power devices. And then comes SI-Wave, which is signal integrity wave, deals with the simulations that are related to power integrity and signal integrity concepts inside PCBs, IC packages, etc. As a continuation, we also have EMC Plus that deals with simulations related to electromagnetic compatibility and electromagnetic interference concepts like conductive emission, radiated emission, conductive immunity, radiated immunity, and even cable harness modeling starting from automotive to aerospace applications. And Charge Plus focus on the simulations that are related to charging and discharging phenomenon like a dielectric breakdown, arcing in air, and also even the lightning effects on the aircrafts. And to all filter designers, there are special softwares, two special softwares from Ansys, that is Cinematrix Filter and NeoEdge Filter Solutions, where Cinematrix Filter will focus on complex 3D filter designs like ceramic filters, SAW filters, SIW filters, and also cavity resonator filters. And then comes New Hertz Filter Solutions, which is dealing with the software simulations that are related to planar filters that are loaded with lumped elements, and also it is very fast because it is being automated with AI. Using powerful answer solutions, one can perform simulations starting from nanometer scale to kilometer scale, that is from silicons to systems. When you want to perform photonic and silicon-based simulations that comes under nanometer scale, Ansys provides numerical packages for the simulations. And when you want to deal with the simulations at the chip level, that is micrometer level, which comes under semiconductor domain, Ansys and Synopsys provides packages related to the semiconductors. And when the simulation has to be performed from millimeter scale to meter scale, answer solutions like SI-Wave, IcePack, Q3D extractor, and AEDT can be used. And for hardware level simulation, answer solutions like Maxwell, Sherlock, EMA 3D cable, MotaCAD are prominently used. And finally, to perform simulations starting from nanometer scale to kilometer scale, there is one special software called HFSS, that is High Frequency Structure Simulator, which is so powerful to perform all these simulations, which has been provided from Ansys. And now we'll move on to how high frequency, like Ansys high frequency technology works. The first process is picking a proper solver. A solver is a tool where you can solve Maxwell's equations, as our electromagnetic problem differs from nanometer scale to kilometer scale. The first solver is HFSS FEM, which is finite element method, which is used to discretize the entire volume, like a 3D model that will be enclosed within a volume. The entire volume will be discretized into smaller tetrahedral elements, and electric and magnetic fields will be solved for each tetrahedral elements and finally combined to provide results, that is electric and magnetic fields. And this solver is best suited for antennas, filters, waveguides, etc., which deals with the complex geometries. And the second solver is HFSS IE, which is integral equation solver, which solves Maxwell's equations in the integral form. And this solver is best suited for large metallic structures like aircraft, uh, satellites and parabolic dish antennas. And then comes SBR Plus, which is Advanced Shooting and Bouncing Ray Solver, which is used to perform simulations related to electrically large scenarios like automotive radar simulations, radar cross section analysis, and even antenna placement analysis. And the next solver is domain decomposition method, which is DDM. When you have a large or huge electromagnetic problem like aircraft, this will be divided into smaller subdomains, and each subdomain will be simulated separately by different computers using their high performance computing technique, which is sharing the network processors and memories, and finally combining the results to and providing it to the one system. And the next step is to provide your geometry into an HFSS design environment, where you also assign your materials, boundary conditions, and also proper excitations, and along with the frequency that you're going to work upon, can be with single frequency, multi-frequency, or broadband frequency, and then excite the simulation, they excite the 3D model. And while doing that, there will be automatic adaptive meshing happening inside. That is where your 3D model, like this microstrip patch antenna, will be divided into smaller tetrahedral meshes. And electric and magnetic fields will be solved for each tetrahedral elements based on Maxwell's equations. But at some points, like the corners of the microstrip patch or edges, and also the feed point, the field variations will be very high, which means the fields are in error. So the software will provide a refinement of the mesh, which means my larger tetrahedral elements will be replaced by smaller tetrahedral elements, and again fields will be solved for Maxwell's equations. So this process is iterative and becomes continuous. It stops only when it reaches the convergence criteria, which means my current S parameter result should not vary that much with my previous S parameter result, where I set my threshold value to the software in terms of maximum delta S. And then comes post-processor. After the completion of the simulation, there are the few steps that we're going to see the results, like in terms of surface current distribution, volume current distribution, and then electric fields and magnetic fields over the surface and volumes, and also radiation patterns in terms of 2D, 3D, and S parameters, and so on. Once a design is completed, if you're not satisfied with the performance, we can move on to optimization process, where you have three steps in this, where first is parametric analysis, where you provide a variable to a 3D model, that is dimension of your 3D model, and vary it from like a smaller value to higher value in a small step size. and pick and perform the simulation and pick up the best one that suits your that accepts the performance of the product. And then second step is providing optimization. You set a goal to the software and software will work towards your goal to optimize your design. And third step is tuning, where you can see instant results like how my design is varying for the certain parameters I provide inside the design environment. And then comes Ansys customization suite. The best example is antenna toolkit, which is present inside AEDT, where I don't want to design my antenna starting from the scratch. Like I can just design antenna within seconds by providing the resonant frequency and also substrate details into it. And then comes multiphysics, which integrates the simulations that are related to electrical, electronics, optical, mechanical, thermal, etc. As I said before, there are some solvers involved in HFSS. First is a frequency domain FEM solver, which is mainly for targeting complex geometries because it uses finite element meshing, that is tetrahedral meshing, as it conforms very well for the complex geometries. And then comes time domain FEM solver. This solver is best for transient analysis, like concepts related to EMI EMC, that is lightning, conducted emission, radiated emission, conducted immunity, radiated immunity, signal integrity, power integrity concepts. And then comes a frequency domain IE solver, which is a solver that deals with electrically large metallic structures and solves Maxwell's equations in the form of integral. And finally comes SBR plus solver, which is advanced shooting and bouncing ray solver, which is for electrically large scenarios like automotive radar simulations, antenna placement analysis, and even radar cross-section analysis. And these are some of the examples where simulations in the HFS are performed, like signal integrity, power integrity, automotive radar simulations, designing of RF filters. And we can also perform RF co-site analysis inside aeroplane, where you have two antennas placed inside a large platform like aircraft, and you can analyze the interactions how between the antennas are taking place with respect to the platform. And then smartphone biocompatibility, where you have different phantom models from Ansys and like head model, hand model, and you can place your mobile phone along with your antenna and even perform SAR analysis, which is specific absorption rate, which tells how much of RF energy is being absorbed by your human tissue. And finally comes antenna placement analysis, where you check how the antenna behaves in a different environment. Yeah. Simulations generally takes place like four stages, starting at a component level, system level, then to platform level, and finally a scenario level. For this, let me take an example of an antenna where I initially start designing an antenna as a single element. And then from the single element, I design an array of antenna. And then I place this array of antenna on a platform like a street light or a car body or a truck, and then analyze its performance, and finally take this to the scenario level where different platforms are being integrated to mimic the real-time scenarios. And now we are moving on to 5G millimeter wave beamforming and phased array antenna design part. 5G millimeter wave generally deals with the frequency, like I have chosen the frequency of 28 gigahertz. And when it comes to antenna array, there are two parameters or terminologies which are inseparable. One is beamforming and beam steering. Beamforming is all about creating a focused beam using antenna array elements, while beam steering is steering this focused beam towards intended direction without moving the antenna physically. Now we are moving on to the demo part. Now I am going to start my design with a single patch antenna. So I'll go to View, ACT Extensions, Launch Wizards, HFSS Antenna Toolkit. And once your antenna toolkit is launched, you will be able to see different antenna types. Now we are interested in patch antenna, which is profit, which is rectangular profit antenna. So click on rectangular profit antenna and provide your center frequency. Our center frequency is 28 gigahertz. So enter the center frequency. And the next step is substrate dimensions. Choose a proper material you're going to work upon. Click on edit, and I'm going to choose taconic as the substrate where you can access it from the material library. So search for Taconic TLX9 and give OK. And the height of the substrate from the data sheet that been provided by company is 0.79 mm. In centimeter, it is 0.079. And yes, once these details are provided to the antenna toolkit, click on synthesis. Once I click on synthesis, you will be able to see the substrate dimensions, antenna dimensions, feed dimensions, everything are updated within seconds. Once this is done, click on finish. This process will import your antenna design into your HFSS design environment with all the pre-processing steps. Like I'll close this ACT extensions. I'll expand the model under the history tree. Like under PEC, we have there is perfect electric conductor. We have coaxial pin, feed pin, and a port cap. And a taconic is assigned to the substrate. And under Teflon, you have the coaxial. And then perfect T is assigned to antenna and ground. And waveport is assigned as an excitation for the coaxial feed. And inside your project manager window, you will be able to see expand the boundaries where antenna, outer coaxial cable, and ground are provided with PEC boundary conditions, and excitation where your coaxial cable cross section has been excited with the terminal port, sorry, wave port, and then expand the analysis where you will be double click on ATK solution where you will be seeing your frequency which we have given at the antenna toolkit design initial step, which is 28 gigahertz, and see number of passes 15, and the maximum delta is, which is our convergence rate, which is 0.02, and give OK. You have automatically two different sweeps, so we'll only focus on one sweep. We'll delete off the other sweep. You double click on S parameter sweep where my antenna is going to provide results from 24 gigahertz to 32 gigahertz. I'm just shortening the span of the frequency and increasing the number of points to 201, and give OK. And then under results, you will be able to see the software is automatically provided results that are related to 2D, 3D radiation patterns, return loss, input impedance in terms of Smith chart. And when you expand this radiation, you no need to give any set up your infinite far field setup. So this is automatically done by software. This is for 3D where your phi will be varying from minus 180 to 180 and theta from 0 to 180 with step size of 2. And then comes azimuth plane, which is my horizontal plane, where phi varies from minus 180 to 180 with step size of 1, and theta varies from 90 to 90 with step size of 0. And for elevation plane, it is the T5 where it varies from 0 to 90 with step size of 90. And theta varies from minus 180 to 180 with step size of 1. This is all about the pre-processing steps. Everything is being done by the software itself. Like we have to check for errors and move on to the simulation part. Go to HFSS. Click on validation check. Check for any errors or warning messages under this. Everything is green, so there are no errors and warning messages. So we'll move on to the next step, which is analysis part. Again, go to HFSS under your menu bar and then click on analyze all. Let's wait for the software to complete the simulation. Yes, the simulation is complete now. Now, the very first thing we are going to focus upon microstrip patch antenna is return loss. Yes, let me check the resonance. Where is the resonance happening? So, right click on marker, add X marker. I can see two values like resonant frequency and also the return loss. My antenna is actually resonating at 26.53 gigahertz with return loss of minus 4.29 dB, which is very low. My performance of antenna is very poor. So let's check for other results also. Radiation pattern, like my max gain of the antenna is 7 dB. That is acceptable. And this is 2D and 3D radiation patterns. So 2D radiation pattern with theta equal to 5 and theta equal to 0 degree. And input impedance, this is trace of S11, which shows my antenna is not closer, like the trace is not closer to the center part of the Smith chart, where there is a lot of mismatch happening inside the antenna. So this has to be taken care. To optimize this antenna, after performing certain optimization process like parametric analysis, tuning, and also the optimization, I have come up with some modification inside my parameters. So I am going to update that dimensions. So go to HFSS, design properties, and I've come up with patch X as 0.35 and patch Y as 0.3, and my feed point that is of Y is 0.12 centimeter. Apply and OK. Now I'll go to HFSS and check for validation. There are no errors and warning messages. Again, I'll resimulate the design and check for my return loss and other parameters. Sometimes these types of errors can occur, but it is our responsibility to optimize it so that we get good product outside. Yes, my antenna has come, like my software has completed its simulation. Let me place this marker at the resonance point, that is sharp resonance point, which is 28.1 gigahertz with the return loss of minus 45.18. Yeah, my antenna is performing very good. And let me check with input impedance. Yeah, this trace is closer to the center point. Then if you want to check with the marker, go to right click on marker, add marker and place your marker on 28.113, whatever resonance frequency you obtained. Like my resonance peak is 28.13, so I'll go and give 28. I'll just edit this frequency as 28.13 and give OK. Yeah, my resonance point is closer to like it is almost so closer to center point of my Smith chart, which shows my antenna has very good matching, which means my maximum power transfer is happening between load and source, and there is a good performance of the device. So then in case of 3D radiation pattern, like in terms of gain, it is 8 dB. Then a 2D radiation pattern, the green trace which represents phi equal to 0 degree, and the blue trace which represents phi equal to 90 degree. Yeah, my antenna has been performing very well. Now my unit cell of the antenna is ready. Now we have successfully completed the design of microstrip patch antenna that is resonating at 28 gigahertz and analyzed its performance in terms of return loss, the radiation pattern in terms of 2D and 3D, and also the impedance matching in terms of Smith chart. Generally, low gain antennas will have broader coverage but will travel only for shorter distance. What about antennas for longer distance? This problem can be encountered by designing high gain antennas, which can provide a shorter coverage but can travel for longer distances. So, the best possible way is to create an array from the single antenna element as shown. Once our unit cell is ready, now we are going to create an array from the unit cell. So to do that, I'll copy paste the design. Right click on the HFSS design, copy and paste it on under your project. Just rename it so that you don't have any confusions. I create array. Okay. So expand this, double click on the design. Again, I think I have to re-simulate the design so that I can work upon this. So I'll again re-simulate this design. Go to HFSS, validation check, and then HFSS and analyze all. Yes, my antenna has completed its assimilation. I'll save it. Before creating an array, I'll go to this model. Some modifications has to be done with respect to the radiation pattern. That is the boundary. First step is to right click on the array model, solution type, and uncheck the auto open region and give OK. Once you do uncheck, you will be able to see a box that has been surrounding the antenna. So this is the radiation box. Expand boundaries, you will be able to see additionally auto open region, which is my radiation surface for the antenna. To create an array, I cannot proceed with this radiation box, so I need to delete this. So delete this auto open region. And then under model, expand the solids and sheets. Like go to solids, you will be having radiating surface and you have create region. Now I'm going to create a region around this unit cell which is bonded. Like there should not be any gap inside along the x and y axis. I'm going to make my boundary bounded, no space around the x and y axis. Like so I'll double click on the create region and remove all the padding distances in along the x and y axis and increase the padding distance along positive z direction and apply and OK. And now you can clearly see my radiation, like my boundary is being very bounded to the antenna structure. There is no gap with respect to x and y directions. And now we are going to provide proper boundary conditions to it. So right click on the radiating structure, have boundary coupled, and you have four options like lattice pair, primary and secondary, and auto identify pair. Click on auto identify lattice pair. And it will be asking for a plane like along xy, yz or xz. We are moving along with xy plane, so click on xy and give OK. Now I'll tell you what is lattice pair boundaries. Lattice pair boundaries or couple boundary conditions are generally required to create the array structures, which means these lattice pairs will enforce periodicity or by um, mapping the fields on the primary boundary towards a secondary boundary with certain phase shift. This phase shift will enforce a certain phase delay along the entire array. So this phase delay will help us to steer the beam in any direction, that is along theta or as the along the elevation angle theta or azimuth angle phi. And when you under boundaries, you can see two lattice pair boundaries are created, which acts as a site wall for the creation of arrays. So when you double click on lattice pair 1, go to phase delay because we need some delay to create steer the beam. So this phase delay can be created by using scan angles, that is along with theta and phi. And if you know the phase delay, you can directly provide. But we'll move with phi and theta, and I don't give the values directly. I'll provide some variable to it so that I can tune it or parameterize in the future. So I give phi scan with unit of degree and theta scan. Again, the degree is the unit, and give OK. Once I give OK, this variable will be added, that is phi scan. I'll provide value of 0 degree only, which comes under angle unit type. So give OK. And this also repeats for theta scan. So it is going to be 0 with a 0 degree with the unit type of angle, and give OK. Once this is done, we'll double click on lattice pair 2, where when you click on this, you will be see automatically it has taken the scan angles from phi scan, theta scan, that is from the primary lattice pair 1. And the next step is to assign radiation to the top and bottom of the radiation box. So I'll go and select the faces. To select faces, I'll right click, change my selection mode. That is, first option will be your selection mode, which is enabled here. Go to faces, click on faces, and select the top, rotate, and escape, and also click on control and select your bottom face. Now my top and bottom faces are selected. So I'll right click, assign boundary, and provide radiation boundary conditions to it. Which means my lattice pair 1 are the side walls for the array, and radiation will be for the top and bottom of the boundary. And then once this process is done, I'll go and create an array. Right click on the model, create array. Only when you provide this lattice pair boundary conditions, you will be able to create an array. This option will be enabled inside HFSS design environment. So click on array and provide, like when you want to give a name to an array, create an antenna array. Just give a name as antenna array. And make it visible. Like my A vector is going to be along lattice pair 1 and B vector is going to be along lattice pair 2 with size of 5 cross 5. I'm going to create a size of array size is going to be 5 cross 5 with number of padding cells as 1. Padding cells are like buffering cells. The geometry will not be present, but they will be helping in the radiation features. So then move on to active cells, where this is how my 5 cross 5 array antenna will look. And then post-processing cell, where I'll make my center antenna to be active, and then click on apply. Once I click on apply, inside my HFSS 3D modeler window, I'll be able to see 5 cross 5 array by clicking on Control D. I'll be able to see the entire view. Under orient, you can click on top. And now you can see there is 5 cross 5 antenna element which is created from the single unit, that is single unit cell, that is single antenna, microstrip patch antenna, which is proof fit. Like the antenna elements will be named as 1, 1, 1, 2, 2, like 2, 1, 3, 1, and it goes up to 5, 5. And the next step is right click on excitations, edit sources. I'm going to excite since we have created this antenna array only from the unit cell, that is one cell, that cell is alone excited, that is provided with 1 volt. I want to excite the entire antenna array. That is, I'm going to provide uniform excitation for the antenna. So I'll provide 1 volt to all the antenna in the arrays. And apply and OK. And then click on analysis part. This analysis part where my entire antenna array is going to resonate at 28 gigahertz. I'm going to reduce this number of passes for saving the computation time, and also the maximum delta is to 0.02. And mesh operations under solution options, I'm going to solve this by domain decomposition, not by direct solver. So click on domain decomposition method. The domain decomposition method is generally when you have a larger electromagnetic problem or huge electromagnetic problem like aircraft, this will be divided into smaller domains, subdomains, and each subdomain will be solved based on the HPC method, that is high performance computing, which shares the network process and memory. And finally combines the results which is being simulated by different domains into single result and provides it to the user. In our case, it is 5 cross 5 array antenna, where each domain will be solved by different cores in our laptop and finally integrated and provided to the user. And this is all about domain decomposition method. And the next option is, yeah, under advanced, I'm going to view the fields as far field. I want to create a far field here. Like my phi is going to vary from minus 180 to 180 with step size of 2. And theta is again going to vary from minus 180 to 180 with step size of 2 and give OK. Yes, this has been set up. Yeah, I'll give OK. Okay, remaining things you keep it default. Yeah, this is all about the pre-processing steps. And now we'll go and check for any errors and warning messages. There are no any warning messages or error messages, so we'll proceed for simulation. I'll go to HFSS and analyze once again. And this array analysis takes some time for us to simulate. So I have a simulated project, so I'll open it. This is the 3D model array element, and this is the gain plot. Let me make this gain plot visible on the array. Right click on gain, show in the modular window, and go to your HFSS, double click it. Yeah. Now Control D, right click on it, plot fields, radiation field, and increase the scale size to 2 and apply and see your radiation pattern looks, how your radiation pattern is there. Like you can still more increase by increasing the scale and close it. Since I want it at the center of the array, I can place some relative coordinate system and then look my radiation pattern at the center. Orient top. And now I'll go to under your draw tab, you will be finding offset option. Click on offset option and got the center array. It's like center element of your array. This is your RCS point where I want my radiation pattern to sit here. Then I'll go to radiation. Under radiation infinite sphere coordinate system, you can use local coordinate system. That is RCS1 and give OK. Now my radiation pattern is setting on the like center to the aligned center to the array. And this is how my radiation pattern looks. Like I have created a focused beam, and these are side lobes of the antenna array. And this is about a beam forming, and I also check for the gain. My gain of the antenna is 21.9. Earlier, my gain of the antenna, single antenna was 8 dB. Look at the change, how the changes happened from 8 dB to 21.9, that is 22 dB. Such a drastical improvement. So this is the um, best option for increasing your gain and also creating a focus beam. Till this concept, it is all about beam forming. Like you have created a focus beam using the array of antenna elements. The next part is we are going to steer this beam, focus beam, towards like any direction, either with its azimuth plane or with elevation plane. To do that, we have to do some post-processing steps, like for to create progressive phase shift. So this can be created using an option called tools toolkit. The simulation is done once you, like before you perform your simulation, you will be having an option called finite array beam angle. So you have to initiate that and click on edit sources and check. Now your edit source, under your excitations, click on edit sources. You will be able to see all your phase shifts and inputs are being changed according to the finite array beam angle inputs, which is not no more like 1 volt or 0 volt here. Now my antenna array has been excited with some progressive phase shift. Once I provide that progressive phase shift, my beam will be steered. So I'll go to HFSS, design properties, and under that I'll be having a parameter called phi angle theta. Okay, so this is my phi angle theta. I'm going to steer my beam along theta axis. So I'm going to steer this beam along 15 degrees and give OK. The simulation is going on. Okay. Only once my simulation is complete, I'll be able to steer this beam. Okay. I'll show in this PPT. Like here, my focus beam is around 0, like theta is equal to 0 degree. This is theta is equal to 15 degree. This is theta equal to 30 or 45 degree. Like my beam gets steered towards elevation angle. Like this can be used for phased array applications. Like at 28 gigahertz, when my applications are dealing with 5G millimeter wave, I can have a focused beam and just connect with the users that I want to click. I don't want to waste my RF energy, the power like spreading as a blanket. So I'm creating a focus beam and steering it according to the availability of the user. And this is all about beam forming and beam steering. And I'll move on to learning resources. Since simulation is fascinating, there are a lot of resources available from Ansys. You can start learning this. The first is Ansys Learning Center, where you can find a lot of Ansys innovation courses related to different domains like electronics, fluids, structures, 3D design, optics, and many more. Where under electronics, you will be having subjects like Introduction to Ansys HFSS, Basics of Vector Algebra, Magnetostatics in Free Space, Electromagnetic wave propagation, and many courses. And under the completion of the course, you will be getting a completion badge where this can be used, this completion badge can be used in your resumes for high visibilities. And then comes Ansys GPT, where you can ask your queries related to your simulations to it and come up with solutions easily. And there is also Ansys Learning Hub. When you have access to Ansys Learning Hub, you will be able to read the concepts related to your theory and simulation part that is being provided by ANSYS. For example, let's say we are going to work upon high frequency electromagnetics. There are concepts like antenna, RF, and microwave, signal integrity, power integrity, EMI, EMC, which will have theory part and also the simulation workflow, how you carry on with your simulations with respect to ANSYS solutions. And there is also free softwares provided for students from ANSYS, which is downloadable from the official website. And these softwares can be used by students to elevate their projects or do their projects with come up with so that they can come up with amazing products. And that's all about today's webinar. And thank you all.